Hi everyone, this is Chandrasekhar. So I'll be representing Team Electra today on the presentation of fundamental geometric algorithm. So these are my teammates' contributions. So firstly, not insertion algorithm will be taken care by me, and surface not insertion and not refinement will be taken care by Sangeeta. Bezier decomposition not removal by Srinija, and at the last degree elevation reduction and some of the design examples will be taken care by Sriram Gali.
Very good.
So let's get right into it, the technical details. So what are knot insertions? Knot insertions, it involves adding new control points to the curve or surfaces and adjusting the basis mathematical functions in order to account for those new control points. So these control points and these knot insertions should be done in such a way that the shape of the curve will be same, uh, but it will be much more detailed after adding more knots. So basically, the more control points we have, the more precisely we can shape the curve and the surface to match the desired design whatever we expect. So this like the vectors and such are already introduced by fellow classmates, so let me just recap some of them here. uh, let u be a knot vector which contains a non-decreasing sequence of real numbers. So here u0 to um represents the knots. Also let c power w of u be a Nerv's curve which is defined on the knot vector we just said. So which will be equal to the summation from I is equal to 0 to n to sub ip of u, p to sub I to the power w. So here p sub I to the power w are the control points which are on the curve. So let us include a new knot u bar which belongs to the set uk and uk plus 1, and if we insert this new knot into the knot vector in order to form the new knot vector u bar, so we can see in the blue region where the new knot has been inserted. New knot has been inserted at u bar of k plus 1. If v sub u and v sub u bar denote the vector spaces of the curve defined on u and u bar respectively, then v sub u is a subset of v sub ur. So thus, like c power w of u will be represented on the new knot vector. It will be in the form of form like this. The summation, it will be in the summation between I is equal to 0 to n plus 1 and n bar I to sub ip of u, q to sub w. So this will be the new control points, new set of control points that we should determine for this curve after adding the new knot. Here n bar ip of u are the pth degree basis functions for the new knot vector. Let's discuss some of the applications of knot insertion. First thing is adding control points in order to achieve increased flexibility in the shape of curve. Also subdividing the curves and surfaces. Last one is evaluating points and derivatives on curves and surfaces. So we already said what c power w of u is defined as. So like actually the term knot insertion generally refers to the process of determining this new set of control points q sub I to the power w in the above equation, where it is represented as like this. Also with the property p2.2 and the new knot vector, new knot inserted, it will be implying like this. So it will start like only when we add a new knot, the changes will take place between uh, the knots on k minus p to up to k and k minus b up to k plus 1. So these are like entire curve will not be altered, only set of only a specific region of curve is altered. So nextly, for all this new knot, so n to sub ip of u will be equal to n bar to the sub ip of u for all I is equal to 0 to k minus p minus 1, as I said. So then n ip of u is equal to n bar I plus 1 p of u for all other points, that is like I is equal to k plus 1 to n. So the above two equation with linear independence of basis function will imply like this: uh, p to sub w is equal to q to sub w for all like I is equal to 0 to k minus p minus 1, but it is equal to p like q to sub I plus 1 to the power w for all the k I is equal to k plus 1 to n. So let's get into the math. So for like nip of u for I is equal to k minus p to k, it will be expressed in terms of n bar ip of u when I is equal to k minus p to k plus 1. So this is what this the below equation represents. So substituting n bar for n bar ip of u, we will get this equation. So it will be like I is equal to 0 to n nip of u like p sub I to the power w, it will be equal to the summation from I is equal to 0 to n plus 1 n bar to sub ip of u qiw. Like as I said, p to sub I to the power w, and it will represent the old control points. Q sub I to the power w, it will represent the new set of control points. So like if we continue the math, like we will get the equations like this. If we like substitute, if we expand the summation, we will get the equation like this. Like ultimately n bar to sub k minus p q to sub k minus b power w, it will be like plus plus plus, like we can see here what it is. So by equating the coefficients and using the knot vector u in the place of u bar, we will obtain like this. If we see here, we will get the final summation to be like this. For I is equal to k minus p plus 1 to k, like we are setting alpha I is equal to u bar minus ui divided by u to sub I plus 1 minus ui. So like 1 minus alpha I is represented like this: u of I plus 1 minus u bar, and u to sub I plus p minus ui. So using the linear independence of the basis functions that we discussed, so we will get the final equation form like this. So q k minus p w, it will be equal to the old set of control points, whereas the new set of control points can be determined using this equation. For all I is between k minus p plus 1 and between k, and all other q sub k plus 1 to I, it will be equal to the like old control points only. Here we already like we can obtain the formula for computing all the new control points. So here it is represented like this. So let's look at an example here. Like we have let's move aside from all the boring math that we discussed till now. Like let's jump into the example so that we'll get more clearer understanding. So here the left picture shows a NURBS curve of degree 4. So the right figure shows the result after a new knot insertion u is equal to 0.5. So we can see that the shape is not changing, but like here if we see the red dots are the q's, all the blue ones are p's. P's are the old control points, and red dots are the new control points that are added to the curve. So here we'll get the final curve like this. The shape is unchanged, but the defining control polyline is changed. So here let us consider one more example where like the degree we are considering it as 3, p is equal to 3, and the vector is defined like this. Here the control points are from p is equal to 0 to 7. So if we try to insert a new knot 5 by 2, we can clearly see that it will lie between u5 and u6. So the k is 5. So thus like nothing changes until 5. So after like q6 we can see it is equal to p5 and q8 is equal to p7. So yeah, it will be shown in the below figure, but like let us first calculate alphas that is required to find out the new control points. Like once we substitute the alphas, we'll get the new control points like this: q3, q4 and q5. Since the control, like the degree is 3, will be affecting only the p minus k minus p control points, that is like 5 to 3. So 5, 4, 3 will be affected. So if you see at the right bottom, we can see that it is a new basis function, like before and after the new knot insertion, while the left side of the diagram, it shows like how the curve is getting affected by the insertion of this new knot u bar. So here we can see that p3, p4 and p5 is getting affected with the q3 and q4. So like oftentimes we will have a necessity to insert multiple knots, like it's not just single knots. So like what are we supposed to do for that? So like we had a previous derivative equation like this: q to sub I par w it will be equal to alpha I pi to the power w plus 1 minus alpha I pi minus 1 to the power w. Suppose this new knot, it will lie between k and k plus 1, initially has a multiplicity s, and suppose like it is to be inserted r times, where r plus s is less than or equal to p. So denote the ith new control point in the rth insertion step by qi to the power w. So then qi r to the power w, it will be defined like this: alpha I r q I r minus 1 to the power w plus 1 minus alpha I r q I minus 1 r minus 1 to the power w. So this is how we define it. So alpha I r is it will be like this, defined like this. So it also represented as a linear equation at the end. So like if s is equal to 0 and r is equal to p, then we can generate kind of triangular table for control points. So here we ignore all the middle parts, and then we will only take the outer ones, that is q I k minus p plus 1 I, like this. It will go till k1 to the power w. So outer control points are kept and the inner ones are discarded. So final control points are obtained by traversing the table in the clockwise fashion, starting at the top of the first column. So these will be replaced by the old ones starting at the index. So therefore we'll now get r is equal to 3, and we use the curve defined like this. So if we insert a knot 3 times, the curve will be looking like this. The shape of the curve is still the same, it will not get affected, but the new set of control points are inserted like this. Here p's are represented by old control points, q's are represented by the new control points that are inserted. Here we can see all the how the new knot is affected with each insertion. We'll move on. So now let's get into the knot insertion algorithm. Like it's really simple. These are the basic steps that we'll use for knot insertion algorithm. First we will initialize the curve or the surface representation. So like our surface is determined by the control points and underlying mathematical functions. So then we'll identify the location to insert the knot. Like this can be determined based on the position of existing control points and desired level of detail, or like we can just take user input. So then we'll interpolate the new control point. This is done using the NURBS interpolation. For this we are considering NURBS interpolation. So next we'll update the mathematical functions. This typically involves like adjusting the coefficient of the function so that the curve or surface passes through the new control point. So like if we want to keep on adding new knots, we will just repeat the steps from 2 to 4 as needed. So this is like coding thing, like we just have a pseudocode for the same. So here we can see that we are getting inputs of the old knot vector and control points and all the s and r k and everything that we needed to compute the new control point and the new vector. Here we are just loading the new vector and saving the old control points. So then we just insert the knot r times. So finally we'll get the the new new set of control points. Now we will move towards knot insertion application. So here we insert new knots in order to increase the knot multiplicity and thereby splitting the curve. When we have enough knots on top of each other, we will have sharper corner. So to split a NURBS curve, the main task is to insert the knots so that the overall shape of the curve remains unchanged. So we can then go ahead and then split the curve. Let's look at an example here. So here we consider an original curve C. So we can then split it at u is equal to half. So then here we can see that it is split into the curve C1 and C2, which are then split at 1 by 8 and 3 by 8 respectively. So that will result in two more curves, that is C11, C12, C21 and C22. Thank you.
So figure A and B, we can show that we are inserting the knots at U dash at 2 by 5 and V at 7 by 10. We are taking an array and applying the attributes with UV minus and UP, and we do it for each row, and we save the unaltered control points in a row and Q row, and we equate it to PW row, and we insert the knot R times in the next loop while loading the auxiliary control points, and we take the alpha in the next loop again for RW, and knot insertion for NURB curves is done in 3 steps actually. Not converting the given NURB curve and performing knot insertion in 4 dimension, and projecting the new set of control points back to 3D form. Can we go to the next slide, please? Yes, and we load the remaining control points in the QW array row, and we give the direction to it, and we point out that the surface knot insertion algorithm should not merely consist of a loop in which curve knot insertion algorithm is m+1 or n+1 times. The computation should not only depend on control points, therefore it can be only computed once and stored in an array, which will enter the loop, and which will before entering the loop it will give m+1 knot insertions. Next slide, please. So we do surface subdivision here.
Okay, let's go back to this knot insertion real quick. Yes, see, we have here essentially a few choices. Choice number 1, we insert only in one direction. Sometimes that's all we want, right? We can just throw in a lot of knots and refine the surface in one direction, and that's perfectly acceptable for application. For instance, you have a cylinder, and the cylinder is linear in one direction. There's no need to subdivide that in the linear direction, so we just insert a knot in the other direction. Or so we can insert a knot in the U direction or in V direction, or if you want to really, if you have a double curved surface, then we probably want to insert in both directions. So the option is there to refine the knot vector one way or the other or both ways. It all depends on what application we are looking at. And the splitting is one example. If you want to split in one direction, then you just insert in one direction. Let's take a look at it. Right.
So we take u and v as integer parameter values, and we insert u with p times and v q times, which subdivides the surface into four surfaces, B-spline subsurfaces. This will together convex hull property, which implies recursive subdivision, and it is applicable to B-spline surface problems. So in the next slide, we can see that uh, the
Mm-hmm.
figure, it is shown in V direction at U 2 by 5. So we control the net of the split surface and the split surface. Splitting the figure with V 7 by 10 with control net of split surface and split surface, we can see that uh, in the we divided it horizontally and vertically. In the next one, we can see it is split into four parts with U 2 by 5 and V 7 by 10.
Right. Now imagine that you're going to shoot a ray into this scene and want to find out where the ray hits that surface. If you shoot it closer to one of the corners, you can just discard like three of these parts and focus on that very small patch. You can also continue subdividing that patch into four parts and see which one is going to be hit. And then continue this subdivision until you find a very tiny, teeny one, and that's you can approximate it with a planar surface, and there you have your reasonably good approximation of the intersection. That's one of the applications that we use this for ray casting or ray tracing in computer graphics. And obviously that's going to be repeated for every single ray. So for all practical purposes, one would basically take that surface down into tiny, teeny surface pieces and check those surface pieces one by looking at the bounding boxes. This is how you can eliminate a lot of unnecessary intersections. But this is a very nice example that shows how well that would work in a complex situation. Very good.
We next go to curve extraction. To extract the isoparametric curve, we must do U naught insertions on each n plus 1 columns of control points. So that is the total of P into n plus 1 naught insertions. So this will give us a Q, which extracting a curve requires Q n plus 1 naught insertions. This figure will show us that. We evaluate the surface with, inserting U P times and V Q times. This causes the surface point to become a corner control point, which results in subsurfaces. And a corner cutting algorithm can be developed with U or V, which is interested first. But was the case for Bezier surface evaluation using de Castro algorithm. This computational complexity is order dependent if P is not equal to Q. So we'll compute S of U comma V, which is either P of Q plus 1 insertions or Q of P plus 1 not insertions. Using the corner point derivative formula, the partial derivatives and normal vectors from all four directions will obtain those, that is left and right for both U and V. Next, we'll learn about knot refinement. So knot insertion itself is inserting a single knot with multiple times. It is often necessary to insert many knots at once. That is called knot refinement. The applications of knot refinement include decomposition of B-spline curves and surfaces into their constituent polynomial pieces, merging two or more knot vectors in order to obtain a set of curves, and obtaining polygonal approximation to curves, and defining knot vectors brings control polygon closer to the curve. This will limit polygon converges to the curve. To state this problem, we can let c power w to u, and with sigma n for ip. This be defined on the knot vector, and let u be the vector, and let x is from x to r, which will satisfy x of I less than or equal to x of I plus 1. These elements of x are inserted in U, and corresponding new set of control points are being computed. Next one, we require no additional maths to develop this algorithm for knot refinement. It is just a software problem, and we find the solutions for this are, we find indices for a and b, so that they will be less than or equal to for all I. From the equations, we can follow the control points from PO to PA minus P and PB minus 1 to N. Therefore, the copy of these are appropriate locations and leaving room for R plus P and new control points. These denote a new knot vector where U is merged with X. These copy the knots of either end, which will not change, and they then go into a loop, which will compute new control points and merge the elements of U and X into U dash. And then the loop will work forward and backward from starting Q to QA to QB. So this algorithm below is from Bohem and Prosh. It works backward and overrides intermediate control points while inserting a knot. U bar is the new knot vector. This is the algorithm for the curve knot refinement. We refine curve knot vector while taking inputs and outputs of U bar, QW, and attributes. Span function use finds, and we give certain limits for that by taking QW and can you go to the next slide? Yeah, we take U bar function and we assign it to the QW array. In next slide, please. And the pictures.
Okay, let's go back to this algorithm. This is called the knot refinement algorithm. Historically, there are two competing algorithms. One is due to Boehm and Crouch. I work with both of them. Boehm already passed away, Crouch is still alive. And another one is called an Oslo algorithm. It was designed by Cohen and Riesenfeld, both of them from University of Utah. They do the same thing, except this algorithm that's in the book and that you presented is considerably more efficient. So this is what has been implemented into commercial systems. But there are probably other algorithms out there, but these are the two main ones that we know of. But that algorithm is by far really efficient and has been used in industry for at least 30 or 40 years. Very, very robust and very, very efficient algorithm. All right, just a historical note.
So these are the cubic and on the values given there, and the middle one is the first midpoint refinement, and the last picture we can see the second midpoint knot refinement of that.
Bezier decomposition. Bezier curves are specified with boundary conditions with a characterizing matrix or with blending function. A Bezier curve section can be filled by any number of control points. The number of control points to be approximated and their relative coefficient determine the degree of Bezier polynomial. Here, the important application of knot refinement is the problem is of decomposing the nerve curves into its constituent polynomial segments. This is required when converting the nerve curve to another spline form. In such a conversion, the first step is to decompose the curve into its piecewise Bezier form. The Bezier control points of the segments are obtained by inserting each interior knot until it has multiplicity p. This is done in two steps. The first step is passing through U and building the refinement vector X. And the second method is calling refined knot curve algorithm defined above. When it comes to decomposing the nerve curves into piecewise Bezier form, the algorithm decomposes the nerve curves and return NB Bezier segments Q, J, K, which is the kth control point of the jth segment. The local array alphas contains alphas with their indices shifted to start at 0. Here we can see the algorithm decompose curve where NP, PW are the inputs and NB, QW are the outputs, where NB is Bezier, number of Bezier segments and QW is control points, which is a 2D array, and QW is the kth control point of jth segment. This is the continuation of the algorithm. Here we can see that we can find the numerator of alpha and compute and store the computed alphas, and we insert the I knots and I times. And here we can see this we find the control points and the Bezier segment is completed. We continue the same process for the I knots. Here the algorithm above is an ideal interface between a nerve system and a system which displays Bezier curves. With modification algorithm, computes the Bezier segments on the fly, pass each one down for display, and overrides each with next. Nothing is returned here. These modifications are removing NB and QW from the argument list and using local arrays QW with the length p plus 1 and next q with the length p minus 1. The next q is used to store the leftmost control points of the next segment. After the segment has been computed, we pass it down for display. And after displaying a segment, we override it with points from next QW and PW, which are the 2D arrays. Here, this is the algorithm for decompose surface. We decompose the surface same as we decompose the curve, and we decompose the surface into Bezier patches so that it makes easy for us, it makes simpler for us to decompose it. And we follow the same method here. Finding the alphas and storing them in numerators and finding for every I knots. This is the same process as shown in the before slides. Here, decomposing nerve surface into Bezier form, we can see an example here. Let's consider a cubic and quadratic surface to be decomposed. In the first A is the control net and B is some surface defined over U 0, 0, 0, 3 A's and 1, 1, 1, and V 0, 0, 0, 2 A's 1, 1, 1, which is a B, and the P. First one is the cubic quadratic surface and second one is piecewise Bezier patch via knot refinement. First one is control points and second is Bezier surface patches. And knot removal. Knot removal is the reverse process of knot insertion. And if from the definition, if it is defined as the process of simplifying the representation of a curve or surface is referred to be knot removal. This is done by removing some of the knots where curvature changes dramatically. As a result, the presentation may be more efficient and manageable. Just like insertion, knot removal is determining the number of control points and removing number of points so that we get a smoother and finer surface. And here, if we see the formula here, CWU equal to NIP UPW, we can say that UR is the interior knot of multiplicity. Let UT denote the knot vector obtained by removing UR t times from U, as U is the total array. It can be said that UR is t times removable if CW has an exact representation of the form CW equal to NIP UQW. And a knot removal algorithm must be able to determine if a knot is removable or not and how many times it is removable. And it should be able to compute the new control points QW. The process for converting a spline curve or a surface in power basis from form to B-spline form is converting the segments to Bezier form, piecewise the Bezier segments together, and remove as many knots as possible. Using the knot vector, all the interior, we can see that using the knot vector, all the interior knots has the multiplicity equal to the degree of yes, and remove as many. We remove as many knots as possible if the continuity of the surface allows. And clearly, the later form is generalization. Here we can see that an example here where we take P naught to P6 points and U0 to U10, where U are the the knots, the total set of knots, where u0 to u3 is equal to 0 and u4 to u5, u6 equal to 1 and u7 to u10 equal to 2. If we remove removing u equal to 1, the first derivative should be continuous, and if and only if this is the first derivative, where the point 3 at stage 0 minus point 2 at stage 0 equal to point by u7 minus u4, point 4 at stage 0 minus point 3 at stage 0. And we find P3 here. And the second derivative is continuous if and only if point 2 at stage 1 equal to alpha 2 into point 2 at stage 2 plus 1 minus alpha 2 into point 1 at stage 2. Point 3 at stage 1 equal to alpha 3 point 3 at stage 2 plus 1 minus alpha 3 into point 2 at stage 2. Where alpha I equal to u minus ui plus p plus 2 minus ui. Third derivative is continuous only if and only if point 1 at stage 2 equal to alpha 1 into point 1 at stage 3 plus 1 minus alpha 1 into point 0 at stage 3. Point 2 at stage 2 equal to alpha 2 into point 2 at stage 3 plus 1 minus alpha 2 into point 1 at stage 3. Here, here we can see the algorithm. If to solve the system of equations, we start with the first and last equations and work forward. If the number of equations we have derived are even, then the final new control point is computed twice. The knot can be removed if two values of the control points are within tolerance. If in case if the number of equations derived are odd, then all new control points are computed only once. The last two computed are substituted into ideal equation. The knot can be removed if the result is within tolerance. We can see that points here from the range 0 to 2, u0 to u3 are pointed at 0, u4 to u6 are pointed at 1, u7 to u10 are pointed at 2. We can see the surface here, the curved surface here. If we have seen the example where we took 6 points and we took 10 knots, where u0 to u10 are knots. Here it is a generalist form of the example where we take n knots.
Let us start discussing about degree elevation. In geometric modeling, degree elevation refers to the process of increasing the degree of a curve or a surface representation, typically with the goal of improving its smoothness or increasing its ability to accurately approximate a desired shape. One common example of degree elevation in geometric modeling is when representing curves. A first degree curve is always a straight line, while a second degree curve is a parabola. By elevating the degree to third or higher degrees, a curve can be represented as more complex curves, such as cubic spline or B-spline curves that can better approximate shapes that are not well represented by a single straight line or a parabolic curve. So, degree elevation can have a significant impact on the accuracy and quality of resulting geometric model. Now, let's see how we can elevate the degree in the mathematical representations. Let us assume Cn of u is equal to summation over I equal to 0 to n ai u power I be an nth degree polynomial curve. We assume that an plus 1 equal to 0, and we can write the nth degree polynomial curve as n plus 1 degree polynomial curve. So the n plus 1 degree curve is shown as Cn plus 1 of u equal to summation over I equal to 0 to n plus 1. Here we are using n plus 1 instead of n, since we are writing n plus 1 third polynomial curve. So summation over I equal to 0 to n plus 1 ai u power I. Now let us formulate the pth degree NURBS curve on knot vector u. U is a vector which consists of n number of knots. So the pth degree NURBS curve is cpw of u equal to summation over I equal to 0 to n ni p of u n into pi. So if the pth degree curve is a piecewise curve, we can elevate the curve to p plus 1 degree curve. So the p plus 1 degree curve can be written as cp plus 1 w of u is equal to summation over I equal to 0 to n cap ni comma p plus 1 of u into qi. Here qi is the number of control points. So from the above curve we have total 3 unknowns, which are n cap, u cap, and qi. Moving forward, this slide discusses about finding the unknowns n cap and u cap. So we can find n cap and u cap assuming that u has a form u equal to vectors u0 to um, which is represented here. So in the above vector form, m1 comma and so on, ms indicates the multiplicity of knots. At knot multiplicity, mi cp of u is c power p minus m1 mi continuous. The multiplicity for cp plus 1 of u will be mi plus 1, which gives us the unknown n cap is equal to n plus s plus 1, and also u cap vector as u0 to u m cap. You can see the unknown u cap since we found the n cap and u cap unknowns. Now we are left with finding the control, which is q. So one of the inefficient method to solve this to find the unknown q is doing the equating the pth degree curve, and p plus 1 degree curve gives us the unknown qi, which is control points. But this is a very inefficient method. So mathematically simpler method involves 3 steps. So the first step is to extract the ith Bezier segment from the curve, and the second step is to degree elevate the ith Bezier segment, and finally we remove the unnecessary knots separating the I minus 1th and ith segments. Now we continue the process until we achieve an efficient curve. Here is an example of how the process follows. First we have a original curve with the vector 0 0 0 0, ua ub 1 1 1 1. U and ub are the knots. We can give any value for the knots. So here we are inserting ua 2 times, which is we are inserting knots. So as you can see, initially we have 6 control points, but in the second step you can see we have 2 more extra control points. In the third step we are degree elevating, and we are inserting 2 more knots with ub, and we are elevating the degree. The third step is we are removing the knots, again degree elevation, and finally after removing the knots, you can see the number of control points are increased, which is total we got 9 control points, but for the original curve we have only 6 control points. So from this example we can clearly observe that the shape of the curve is not changed if the number of control points are increased. This is an example for curve degree elevation. From this example also we can see that as the number of control points increased, the curve became more smoother, but the shape of the curve is not changed. Here is an example for surface degree elevation. We have a original surface curve with vectors u and v as shown here. As you can see, the final form of surface degree elevated by 6 in u direction and 7 in v direction. So in the final curve we can see the surface is more smoother than the original surface without changing the shape of the surface. Moving on to degree reduction, let us assume C of u equals to summation over I equal to 0 to n ni comma p of u into qi to be the pth degree B-spline curve on knot vector represented as below. So C of u is reducible if it has a precise representation of the form C of u equal to C cap of u, which is equal to sigma over I equal to 0 to n cap ni comma p minus 1 of u into pi on the knot vector. The above knot vector clearly shows that u cap equal to a comma and so on a, and from the above knot vector we also receive n cap equal to n minus s minus 1. So we found the unknowns u cap and n cap. To find the control points, we use 3 steps, which is extract the ith Bezier segment from B-spline curve, reduce the degree of ith Bezier piece, and remove unnecessary knots. Here is an example for degree reduction of a B-spline curve. This is the original curve with 9 control points. In the second step, the first Bezier segment is extracted, and the first Bezier segment is degree reduced. Second Bezier segment is extracted and it is degree reduced. The first interior multiple knot is removed twice. The third segment is degree reduced, and the second interior multiple knot is removed twice. So here the dotted line represents the original curve. You can see the error between the original curve and the final curve, which is received after removing the control points. In the final curve we have only 6 control points. Bezier degree reduction. Let's C of u equal to sigma over I equal to 0 to p bi comma p of u into q of I be the pth degree Bezier curve, and it denotes its degree reduced counterpart by C cap of u equal to sigma over I equal to p minus 1 bi comma p minus 1 of u into pi. There are 2 cases for the p, that is even and odd cases. You can see the formulation for p is even case and p is odd case. So this is one of the example for p equal p is odd and p is even case. So for p is even, the maximum error occurs at u equal to half. For p is odd, the error is 0 at u equal to half, and it has peaks a bit to left and right of u equal to half. As you can see in the left figure, which is p is odd, there is no error at u equal to half, and it have 2 peaks on both sides. For p is even, you can see the error is maximum at u equal to half. These are a few design examples of knot insertion. We'll do a small example of a knot insertion in Blender application. First we select all the existing components and delete them. We need to add a Bezier curve, and once if we enter into the edit mode, we can draw a Bezier curve. So let's delete this curve and draw a random Bezier curve. So if you try to move this Bezier curve, you can see most part of the curve is moving if I move the Bezier curve using only one control point. We can increase the depth of the curve so that we can see the curve clearly. Now let us do the knot insertion. We need to control like select the curve, the whole curve, and subdivide the curve so that it inserts one control point. In this case it inserts one control point between two existing control points. So if we try to move it now, you can see only the one part which I am moving is moving, but in the before case most of the part of the curve is moving. If I try to increase the number of control points, when you try to move this part of the curve, you can see very precisely we can move the curve whichever way we want. So this is a simple example of knot insertion.